During all this course, we had this challenge which exists when one wants to apply traditional scientific methods to human sciences, social and human sciences. On one hand, and they were actually both parts of the paradox of the dilemma were expressed by Karl Popper, one of the gifts which the human sciences gave to the exact sciences, in the sense of guiding us towards how science should look like and how science should be made. Next to Wittgenstein, he is a real help for making science. And he said, look, science is the art of systematic oversimplification. But on the other hand, he also said, scientific statements are by definition falsifiable. And I explained at the beginning of the course what it means. It means they may be wrong, and they are usually, eventually, proven to be wrong, or at least not exact. And this is what the scientific progress is all about. Now, the problem is that in the case of electrons, they fulfill very strict and fixed laws. And one of the leaders in physical scientists, maybe the greatest physicist alive, Mary Gell-Mann, he said, imagine that the electrons would have a conscience. They would be like people having to decide and being capable to decide. What a nightmare it would be. Well, more or less, this is what happens in social sciences, in economics, in politics. There are some electrons there, except that they do think, or think that they think. So there is this problem of how to bring together the fact that we have to oversimplify, but on the other hand, make predictions which are precise enough to be falsifiable. And we have come with, during this course, with this solution, this proposal, that actually, if you are thinking about systems which are made out of many individuals, like the politics systems, the economic systems, the social systems, then in order to get phenomena which are not just about a couple of people getting into trouble or things like that, but in terms of what happens to the entire system, to the society, then you need to have some kind of amplifying process. Now, understanding the emergence of collective macroscopic phenomena, which is in fact what one is interested in when one wants to take decisions which are at the level of the entire society, implies, and it might be sufficient for understanding it, just understanding what are the amplification processes which bring from the microscopic random events to macroscopic entire changes. And this is what we more or less did until now. And we called this occasionally autocatalyticity, which means this kind of reinforcing mechanism. You can have reinforcing by entities which are involved generating similar entities, which is in the kind of in the sense of reproduction. When you have a certain population in a country, and we have discussed it in the context of the logistic equation, you can have effects causing their own causes. You can have a contagion, like we had in the case of percolation. You can have what we'll do today, the whole reacting on its own components. And maybe knowing that this is what I'm going to teach today, I mentioned Wittgenstein and all this school in Britain, which were for the beginning of the 20th century, they were very much interested in this kind of paradox which appears in logics and which culminated with the theorem of incompleteness of Gödel. which essentially saying that in the moment that you allow a system to become an element of a system, or even an element of itself, then you have a system which is essentially logically not closed, and you have a universe which is transcending the crystallized, petrified structure of logics. It becomes inconsistent, but of course in time we don't mind that it is inconsistent. But I'm not teaching now the theory of Gödel, and neither of Wittgenstein or of Whitehead and Russell. I'm just making the comment that what I'm going to speak today is in some sense exploiting these loopholes in the construction of logics. We also spoke a little bit about the inhabitants affecting their medium, and especially about, like in the AB model, and especially the inhabitants, the bees, selecting their medium. Which is an interesting twist over the usual selection of Darwin mechanism. So in a sense, you might this way of thinking was a little bit delayed in its acceptance by the wider scientific society, because somebody would ask, you see, somebody would ask, but why there should be such laws? It's not like the laws of Newton, which you just experiment and you see that is so. It's a statement about this kind of autocatalytic processes being very generic. And the answer is the following. It might be that not all the processes and not all the properties of the systems are autocatalytic, but the ones which are not, we don't see them at the macroscopic level. And therefore, it is in a sense by some kind of natural selection applied to the very laws which govern the systems, that the laws which are have this autocatalytic property, which has the property to amplify microscopic random processes to macroscopic phenomena. They are the ones which we are observing in nature. The other ones are not observed. It's not that they don't exist. They are not realized. So this is a kind of visual way to express what is the kind of situation in which you have some individual behavior. If it affects the if it has collective effects which are feeding back on it, then you can have an entire evolution which we have described.
Can you give an example of that?
Yes, now I have a lot of examples. One of them is the Gaia hypothesis. Who heard about the Gaia hypothesis? It is now very modern, because people which are pushing the green agenda, the agenda of discussing the warming or the cooling of the planet, they find this kind of models as appealing. It says that the biosphere and physical component of the Earth constitute a complex adaptive system that maintains climatic and biochemical conditions on a trajectory that is optimal for its own existence. And the addition which made this modern today is that some people say, yes, this is true, except for the human being, which is a scoundrel in this equation, and it is in danger of spoiling this optimal trajectory for one's own existence. So Lovelock, he invented this very many tens of years ago, probably 50 or something. And it says that this is the example, that the plant, animal, rocks behavior, they influence the Gaia, the entire system, and then the entire system feeds back on them, and then you have the Earth thriving. Another example, which in fact very close to the AB model, is the example initially suggested by Kaufman, in which the systems, molecular systems, if they are complicated enough, if there are many enough chemical reactions, then you'll always find some kind of chain of chemical reactions which is autocatalytic, which is sustaining itself. And this is how what metabolism is postulated to be. And many people, in fact, have studied it, and they even made maps of the different reactions in the metabolism and showing that it has this kind of properties. So some chemicals A, they favorize chemicals B and back. And in a sense, our AB model was a simplification of it. There are examples since even longer times. One of the founders of the science of psychology, I think it was in the 19th century, said that the situations that men define as true become true for them. So you have this kind of autocatalytic loop, of this kind of feedback loop, in which the perception of a reality and the reality itself, they become the engine of some processes which in the absence of this perception feedback, they would look completely different. In fact, returning to Karl Popper, he also thought about this system in which he called the Oedipus effect, because he says in the Oedipus story, and in fact in some other ancient Greek tragedies, the prediction of a certain event, because people are aware of this prediction, of this, it influences their behavior in a way that, in fact, it accelerates the evolution of the system towards the self-fulfillment of the prediction. So this and at some stage, Karl Popper said, I thought that at the beginning that this property of this kind of feedback of the prediction on the system itself distinguishes the social from the natural sciences, in the sense that, in the sense in which I spoke before, that the electrons, of course, they don't know anything about predictions. However, he said, no, this is actually, in fact, not true, because even at the level of molecular biology, where you cannot speak yet about conscience or things like that, then the expectations often play a role in bringing about what has been expected. So this again touches one of the great mysteries which the AB model and some other models in this course were trying to touch upon. How does one get from a regime which is totally causal, in which the past is influencing the present and the present is influencing the future, to a situation in which the future is influencing the present and the present had influenced the past through this kind of expectations. And when I say these words, they seem very far away from mathematical realization, but if you remember what we had, this kind of adaptive island in the case of the AB model, then it was quite a realization that this kind of pretty abstract and subtle effects are in fact tractable in a very precise and scientific way.
I don't understand.
Yes.
The future is supposed to affect the past?
You see, there were these bee islands which were behaving as if they wanted to live, yes? They were following the A's. It looked like, if you look at the behavior of the island, not of the individual bees, which don't care if they die or not, or don't have any way to express their fears, or even if they had any, but they don't, because we created them. We know exactly what they do. Yet the islands, they behave in a way, in an adaptive way, which is essentially following, searching, and following and exploiting the random fluctuations in the medium, which is the random motion of the A's, which is what we are doing too. So in a sense, the AB model, in the same way in which we are made of molecules which don't want anything, and they don't have even the concept of survival, and out of a sudden the concept of survival, and immediately when you have the concept of survival, you have the concept of wanting to survive, or things like that, which is future acting on the present.
But doesn't that imply an awareness?
That's the point. That is the point. You are asking this, and if we wouldn't have the AB model, then I would say, I don't know. But now I know, because I created this model with these little A's and B's. The A's and the B's don't have any awareness. And still we have this situation in which the B islands are surviving because they are adapting themselves, because they are searching for the fluctuations in the A, because they are following those acting upon these fluctuations and exploiting them and succeeding to survive much beyond the level at which the naive equations would tell us. That's the point. So indeed, this kind of very simple model has something to say about maybe the emergence of what we perceive as conscience or things like that. I avoided to do that because I'm not a specialist in that, at least not from the other side of the problem, and therefore, of course, I fell into this other problem of having too mathematical description of it, exactly because I wanted to avoid speaking about things which I don't really know. So, so we have also the concept of reflexivity. And I will go a little bit faster because, and of course there is, who heard about the concept of memes of Dawkins? It is also an expression of this kind of, so I think that there are enough examples. I prepared more, but I think I'm just flashing them, because in fact some of them appeared in previous lectures. So now I'm going to discuss, now I'm making a switch. Back to, as I said, to things which I know how to express them in a precise way. Maybe not very mathematical, but at least in terms of conceptual schemes which are relatively clear. So I'm going to describe how some macroscopic processes are taking place, you know, in terms of this the interplay between the microscopic effect and the macroscopic effect. So in this case, in the case, there is a very old theory about how price is formed in an economic system. You are an economist, I think? Yes. Okay. So now you will see a very may I say, original way of presenting the market price formation, which was invented in the very beginning of the classical and neoclassical periods of economics. But you will see that we can understand nowadays better, especially because in their case they were assuming decreasing returns, and nowadays we have a lot of increasing returns. Whoever doesn't know yet what is increasing and decreasing returns, I will explain in a short while. So, so in this case, the macroscopic quantity is the price, the market price. There is one price which is true for the entire market. Of course, if you are not in the same place, it's different, but this is at least the approximation which Marshall and Walras have used. On the other hand, there is another quantity which is the number of units that have been sold. And of course, each of them was sold to another individual. So this is a microscopic element. And the two elements, the price and the number of buyers, of course, interact. And this is actually what they say. They said, and as I said, we are going to modify this assumption of theirs, which in their case was very crucial. And in fact, when we will modify it, we'll get much more interesting effects than what they were looking for. They were looking for just explaining how the price in the market is stabilizing. But of course, in such a world like ours, in which we have so much instability, what is really important is not how the price stabilizes, because in fact it doesn't, but how the price does fluctuate so much and eventually gets even into crisis. So in order to get the price stabilized, they used some assumption, which in fact I think it was postulated even by somebody before them, probably Mills, which is the principle of decreasing returns. Which essentially says, his example was the example of somebody having some orchard for apples, and the question, and he could produce 1 ton of apples per year. And now suppose that the market is increasing, people want more apples. Now he has some corner in his garden which is full of stones and things like that. So in principle he could use it, but first of all it will be with less productivity, and he will also have to work on the stones there. Therefore he will have to charge more. So we are speaking not about him increasing the price just because he wants to make more profit. This is not taking into account by the economics, because they say that there is enough competition that people cannot act as if there is a monopoly. But they say, no, it's really true that if you want to produce more, it gets less and less easy. Of course, this is not true at all when you are producing some kind of, let's say, Windows software, in which just making some more copies of the software is not a big deal. But this was definitely the case at their time. And the other thing was that, so this was the dynamics coming from the macroscopic point of view, how the supply price was coming. On the other hand, there was this quantity, how many people would buy at a certain price. So if you, for instance, out of a sudden the bread becomes in a country very, very expensive, then they will not buy bread. They will buy potatoes, which is a very good substitute for the bread. And therefore you have this decreasing function of the amount of quantity which is bought as a function of the price. So you should think about this line, this red line, actually as if this is the x-axis and this is the y-axis, because it is the price which is deciding the quantity. But since I want to bring both effect on the same graph, then I must make a choice that one of the x-axis is vertical and its horizontal part it's the y-axis, such that you have both on the same graph, both the function which decides what is the price as a function of n, of the quantity, and what is the quantity as a function of the price. By the way, there are exceptions to this line going down too, but I'm not going to discuss about it. Somebody got a Nobel Prize for that. So we have this kind of feedback loop in the following sense. You have, these are power, actually these lines, I take them on a logarithmic scale as always, so instead of curves I have more or less a straight line. I assume that they are power laws. They are not always power laws, but in enough many cases that I will just for illustration use this, at least at the beginning. Then we'll get more sophisticated. And then the dynamics which Marshall and Walras had in their head was actually a little bit different for each of them. They didn't have exactly the same position. But for the present thing is the following. Suppose that I have this kind of two lines, the one of the supply, the price, and the one of the demand as a function of the price. And now I start with a certain number of buyers. And now I see that actually the price, the supply price for this number of buyers is pretty low. So the demand will increase because for this price there will be more people which want to buy it. So, but once the price once the number has increased, then also the price has to increase. So, so I go on this line. So you see, these two lines are helping me to make some kind of a history of what is going on, how the price is converging to the fixed point, which actually is the intersection of two lines. In the case, I think, of Walras, he called it tâtonnement, with its groping. In the case of Marshall, I don't remember the name. But the point is that if you start with a certain n, which then this fixes the price, and then the new price fixes the new number of buyers, and now this number of buyers fixes the new price, and so on. And you see that in certain conditions, this process is converging.
The one thing, I think it's supposed to be the other way around, the arrows. Because at first you supply the number of n0, so you would sell.
That wouldn't be a problem.
You can't bring more supply if it doesn't create a supply. It can't go.
If you want, there is no problem. I can start with a certain price. It depends where you start. You can say, look.
You can't sell more than you create.
Okay, so you can imagine that I started here with this price and I started here. So in place of starting with n here and continue like this, you can say I start with this price, and given this price.
No, but
sorry. And given this price, I get this n. And
then it would go up. Yeah, that's what I was saying.
But in any,
but it would go a different direction, the arrows. Instead of going right and then up and then.
Okay, at least at the beginning, it's conceivable to say that first. I'm not that sure.
It would be up, so it would be over the demand curve.
Yeah. In any case, it's clear that wherever I start with the point on these curves, then it will, in that conditions, will converge. By the way, I'm going to discuss now the conditions, in fact, it doesn't converge, and you will see this. So, for instance, in order to make the mechanism clear, I'm discussing now in a more cartoon way the situation in which, in fact, the price does not depend on the number of buyers, which is not an absurd thing, because, for instance, if already there are a number of cars in the depots waiting to be sold, then their price is not going to change over. So then what happens is the following. You can imagine that these people with this height, the height of these people represent what the economists call the reservation price, which is the highest price which that person is willing or capable to buy. And suppose that there are some cars now appeared, and this is the price which they have. And if I order the people in the order of their height, then there is knowing what is the dependence of n on p, which is essentially the curve which describes their height. allows me to tell how many people will buy. So what I'm doing now is just an explanation of how this kind, another explanation of this kind of loop. This time it is so explicit that there is no doubt anymore. So this one, it has a height, has a reservation price, which is higher than the price. Therefore, he will buy. But also this one, the red line. It's about the implicit price which he is willing to pay, being number 2. So here I have n, this function, it's n as a function of p. But don't remember, n is, in my case, the x-axis. So this is partly a reason for the confusion, because I have both n and p acting as x-axis and y-axis. So, but in this case, since p is constant, the confusion is less. So this one will buy 2. And this one has a head a little bit above the price, so he will buy 2. However, this one will not buy anymore because the price which he can afford is less. So we have this 1, 2, 3. This number of guys which bought are essentially a realization of this rule that as the price goes, that n depends on the price. If the price was lower, in fact, if the price decreases, then the number of adopters increases. For instance, this was the old price with 3 people. But now if I lower the price, then you see that there are more people which have their heads above this 2. And so so this is an example of this equation which I wrote, that the number of people, or if you want the fraction of people in a community which are going to buy, are going with this kind of decreasing function of the price. That is their view. So we have this kind of feedback loop, which in fact is in a sense a negative feedback loop, because as the price increases, n, the number of sold things decreases, which would bring to a lowering of the p. If n increases, then p, the implicit p, will decrease. You see, or from here, if n decreases, then p will decrease too. So this is stabilizing. But this is in the case of what I call the decreasing returns. However, as I just commented some minutes ago, we live in a world in which very many of the products are fulfilling an increasing returns rule, in which this exponent is negative, and therefore, whenever you have more products sold, you can afford to lower the market price for that. And in particular, I gave this example of software, but it's not only for software. So instead of having this kind of situation in which p is an increasing function of n, we have this kind of situation in which p is a decreasing function of n. However, we can study what happens with this kind of a graph. And what will happen is, of course, that the sales will keep increasing only as long as the market supply price is below the price which is implicit for the number of buyers which you have now. You see, again, I'm obliged, in order to compare the two functions, p as a function of n and n as a function of p, to think also in terms of what is the price which ensures a certain number of n, and I'm comparing it with the supply price, and I'm judging what happens with the process. So if the price decays, so we have that the price decays as the number of adopters increases. On the other hand, the price decreases as, on the other hand, the number of adopters increase as the price decreases. So this is already a positive feedback loop. Is it clear that it's a positive feedback loop? Because that's the entire point, that now we have the possibility of having a process which is sustaining itself rather than being suppressed by itself. So essentially, what we have these two functions. They are exactly the two functions before. Sorry. They are exactly the two functions before, except that now I'm showing it with people. So again, it's in a sense solving our mismatch between interpretations, because now it's in an explicit way. I'm saying that as the number of buyers increases, this is the price. So if the number of buyers would have reached this guy, then the price would be here. On the other hand, I have the curve which describes what are the reservation prices of each of the of the guys, and how.
It's not an equilibrium yet.
Exactly. Now, of course, they are not in equilibrium. Meantime, they didn't buy anything. Now we are going to see what happens. So I'm starting with P0, and the first guy buys. I'm sorry, the first guy buys. So I went here from this black line. I went here, and this is because it was allowed by the price for this guy to buy. In the moment that he bought, the price went down. But since the price went down, this guy can afford it too. Actually, he could afford it even before, but he definitely can afford it now. So he according to the fact that n is p to the minus mu, and the price was the market price was this one, he is willing to pay a higher price than the actually market price. And on top of this, the market price now goes even lower. So you see, I'm now repairing maybe our clash, because right now it's very explicit. So now I have the market price here. The guys which bought, they are this. And this next guy, which maybe couldn't afford, I'm sorry, this guy, which couldn't afford the initial price, because the price went down, he can afford it now. Does he? Yeah, he does. He's above this line. And the price, and he buys it. And because he buys it, then I have to update the price, the market price, which it goes down. And because of this, this guy can afford too, because this red line is still above the black line. Until when? Until they cross. And this one still can buy, but this one cannot anymore, because you see the market price did go down, but he goes down slower than the willingness of the people to pay. This relation between n and p. So this is the price at which the process stops. So you can describe it by this kind of process, in which this is n and this is p, and I start with a certain value, let's say, of p. By the way, indeed, here I started with a certain value of p rather with a certain value of n.
That's okay. What you did before was not.
Yeah. No, this is what I'm saying, that here it happens to be correct. And But again, the important thing is that you have this kind of convergence. But of course, this convergence depends on the fact that the slope of this function, n as a function of mu of p, which is in a sense now on this graph n is x, but it looks in this way. It's above this line, which is p as a function of n. So it converges. If on a logarithm scale, if those things were power laws, then what you see is this kind of situation in which, again, I started here, but you can imagine that I started here and at a certain price. And it converges, and interestingly enough, it converges from both sides. So even though I'm now in the regime of decreasing returns, in which the price is actually decreasing with n. So if the price decreases mildly with n, I'm still capable of recovering the Walras and Marshall theory of convergence. However, let me make one more. But in the case in which this one has a higher slope than this, in which I'm starting with a price which is not affordable to any of the guys, including the highest one. And this can happen. For instance, if you want to push some green for instance, in the case of green products, they cost more to develop. So at the beginning, their price is very high, and people don't afford. In fact, we had an example in this country in which people have tried to introduce some environmental electric cars, and they failed because the price was double. So in that case, in some of the situations, which happened only partially here, you can try to subsidize to make this difference between the actual price and the price which the guys are willing to pay. You can subsidize that. The state can subsidize. And the interesting thing on this graph is that once you don't have to subsidize forever. You have to subsidize only until the two graphs are crossing. In the moment that you get here, in which the implicit price decided by how many have bought until now, in which you have this price here corresponding to the number of people which have already bought higher than the actual market price. So these guys are above the market price, and therefore they will buy. And as they buy more, the market price goes even lower. And therefore, from here on, the process is self-sustaining. You don't have to subsidize anything. As more and more people are buying, the price goes lower and lower, and then the process goes until the entire population, we'll see that not always the entire population, adopts the new product. So the problematics which, one of the problematics which we'll encounter in this lecture is this problem of how to schedule the subsidies of new products. In order, so in this case, if you start, if you force, you see, maybe here indeed it's more appropriate to start with n, because you say if I force the adoption by giving people the money, or maybe even, as it happened a little bit here in this country, imposing to some companies to really pass to that new product, then in the moment that I'm beyond this point, then in fact the process continues until eventually the entire n goes to infinity. Now I'm going, on one hand, I'm going in great detail on that, but because I want you to become familiar with this way of describing the process, in this bouncing between n as a function of p, then p as a function of n, then n as a function of p. So please confirm that you are following this. You are following this. You are also following this. this is why I went with these people, making it very explicit. So essentially what happens is that, in fact, this dependence of P of n was considered, there is a misspelling here, it's Solow, it's his name. He attributed at the time this lowering of the price by saying that it's learning by doing. More products you produce, more you learn how to do it more optimally, and therefore you can afford the price to go down. And N of P, it's basically the Pareto. You can imagine that people have different wealths, and therefore they can afford, you can ask how many people have wealth higher than a certain value P such that they can afford to buy the product. So essentially N of P, that power law which decides how many people can afford a certain price because their price, which are capable to pay, it's larger than that. It's essentially Pareto, while P of n is this theory of Solow. You have a question? And of course, this intersection of the two lines is saying that if I have the function n of p, and I have the function p of n, if I stop these iterations whenever I have that p of n of p, it's equal to p. So, these two functions are crossing, which is equivalent to asking that n of p of n is equal to n. Now, the problem is, of course, that nobody is really capable of ordering people in the order of their prices. So basically, you can have a situation like this, that there are some possible buyers of the car, but they don't even know about the car. Because in order to learn about the car, you remember we had this percolation thing, the knowledge about the car has to reach them. So this is what we are going to address now. To graft this theory of price formation, the neoclassical theory of price formation of Walras and Marshall, on the percolation transition, which we have studied already. And by doing that, you remember that essentially it means that we are very much widening this theory by including many other things, not just adoption of some product, but maybe the creation of innovations, of the adoption of some other things. So I remind you that in the percolation thing, we have a situation in which, suppose that the red guys are the guys which are above the price, the market price. They are willing to pay even prices higher than the market price. And suppose that some of them already bought. Then the other ones which are in contact with them, they are going to buy. And you are going to conquer a very large part of the system. Not all the system, because there are going to be branches which are still not touched. But in certain conditions which we have discussed before, you have a very large part of the system which can be conquered. And of course, this depends on the price. For a very high price, there will be very few red guys, and they will be sparse and will be below the percolation transition. And if the price is low enough, then there will be many red points, high density of potential buyers, and they will adopt. So here is a figure again. I tried to make it very intuitive. The question is whether I succeeded. This is a square lattice as we had, but now I'm taking it in a perspective, in 3 dimensions, because I have this, I imagine that there is a plane just above the lattice, which is saying what is the height of the market price, and the height of the guys is still how much of or they want to pay. So now, since they are they are at different levels, then it's difficult to understand who is above and who is not. So the ones which are above, they have these heads which are whiter because they are above this plane. Okay. So I start. This is a plane which is parallel to the lattice and which has the height of the market price. And the guys, suppose that I start with this guy buying. Then this one is a neighbor of him, and it also has a reservation price which is higher. So he will get contaminated. Because of this, the price will go down. And I don't remember if this one was above or not, but definitely now he's above. And but he's not a neighbor of this. You see there is somebody in between them, so he's not going to buy. But because this have bought now, so just a second. So it was like this. It was this kind bought, then this guy bought, and those guys become but this one, even though it's much smaller than this one, it is now above the market price, and it is a neighbor of somebody which so he will buy. And because and this other guy buys too. Because of they buying, now the price went down, and these guys yeah, but again they are not relevant. So let's see. I think that because they bought just a second. They bought, so now it goes down again. And then this one becomes likely to buy. And this one too. He was red at the beginning, but now he's above, his head is above, so he can buy. But this one too. So they buy too. And then it goes down again. And then, and even without going down, because this one got contaminated, this one can get contaminated, which was waiting since a while. And now that's it. Everybody else, which is a neighbor of these guys which adopted, even after the price went down because they adopted, they are stuck. So you see, in the end, what happened is that we got much more sales than we expected, but it's still not the entire lattice. So in order to give, and this is the beauty of what I'm trying to, the beauty which I'm trying to uncover. Until now, I made use this animation. You might like it or you might not like it, you might get convinced or not. It's a story. You can buy the story or not. But because we understand already in quantitative terms what's going on with the percolation, then you'll see that this system, which I treated at the level of the stories, can be treated actually very precisely and to come out with predictions about what is going on in such systems. So in order to do that, please remember the following thing. That if I have a certain density of potential buyers, this doesn't mean that they are becoming buyers for sure. And it's a more complicated thing. If for a while, if the potential buyers are below a certain density, then I'm not getting any significant thing. I'm stopping like I stopped in the previous case at a slightly larger value, but still irrelevant for an infinite or for a very large system. So instead of using the straight lines which were invented, which I was using on the logarithmic scale for this Walras Marshall kind of thing, I will have to use these functions. But I know them. So I have a chance to actually solve the problem, and in fact the problem is solvable analytically. Because, for instance, you remember that we know how n depends on the density. It depends like 1 minus rho over rho c to some minus gamma, and gamma and rho c depend on the details on the lattice. In the case of branching lattice, we could give an exact result. So whenever we'll see a straight line characterizing n as a function of p, we will use from now on, in place of the straight line, this a line which comes from the fact that in fact the n does not depend, is not proportional to rho, but it depends in this particular way. So we'll have in the end this kind of feedback loop, still which can be positive or negative feedback loop, and you'll see that in different regions of the parameters we'll have all the possible cases. What is called the phase diagram of the model becomes quite complicated, and exactly because of that, quite valuable in terms of telling policymakers what is to be expected, what is the kind of schedule of support, let's say, of a green product such that it will succeed. Because it might be that this green product, this electric cars which were marketed in Israel, maybe if with a more thoughtful way of subsidizing it, it would have succeeded. Maybe with more at the beginning and less at the end, or maybe more at the end. We'll see what is the optimal schedule for subsidizing in order to have but in the meantime, let me be more explicit about this feedback loop. Do you already, by just inspecting it, realize, or should I say the word? I say the word. Okay. So suppose that I have a certain P. This P decides what is the density of susceptible sites. The density of susceptible sites decides what are the number of sold ones, which is not at all the same, especially if rho susceptible is very much lower than rho C, then you have a very limited number of n's, okay? Even though you have, in principle, a large density. And if the system is large enough, density means a very, very large number. But here we are getting a finite number as long as rho susceptible is less than rho critical. Now, once I know what is n, then I can plug it in the product, because I said that if I have more sales, then the product goes. In fact, here it's still up. It's in the case of how is it called? Decreasing returns. If you have on this particular thing. But we'll also consider, of course, the relevant one for nowadays, which is decreasing returns. And then once you have a P, then the new P will influence the new rho, and the new rho will influence the new n, and this is our feedback loop. So now we have to remember that if I'm thinking about rho, it's somewhat related to the price, and this is a number of actual buyers. But instead of the actual buyers, from now on we'll which were in the past the number of actual buyers were equal with the number of buyers. It was a straight line with 45 degrees. But now we have this kind of situation, and therefore instead of having n as a function of p, this decreasing straight line on a logarithmic scale will have this kind of dependence of relation between the number of actual buyers and the price. Okay? So now, instead of having, instead of applying this kind of convergence procedure to straight lines, I will have to apply it to this one, which is still the straight line, and it's still with this increasing of prices as a function of n, with the old neoclassical economics position that there is decreasing returns. But even with that thing, what we have here is that instead of having a straight line here, we have a very flat line here, because it corresponds to the critical density, which has a critical price. So you might think that, you might think that, okay, so I exchange one function to another. Well, this is not at all so. And in fact, the intuition that is not at all so, it what brought us to invent this model. I think I mentioned to you, I was visiting my coworker in Paris, and he returned from Santa Fe, and he said, look, these people are trying now to understand why there are these very large fluctuations in the sales of movies, which apparently they are more or less the same. And essentially, this is the answer to it. That instead of having this straight line, you have this kind of line. And then what happened here is that if you have this line bended like this, then the slope here and the slope here are different. Because of this, with the slope here, the process is converging. But with the slope here, the process is actually diverging. So there is some kind of region in which, let me show it here. Yes, sorry. There is some limit cycle which in which the prices keep fluctuating within this cycle, even though you would think naively that they must converge. Well, they must converge if you really believe the procedures of Walras and Marshall. But you have this kind of thing. And because of this, you expect very large fluctuations in the buyers number of buyers and in the prices. Moreover, you might ask, okay, but who tells me that this intersection has to take place exactly in this region? Well, there are 2 points. First of all, this region is very large because this is, it's very flat, and it takes me from finite values to essentially values which are of the size of the system. But on top of this, there is the behavior of the producer and of the buyers, which actually self-organize the system and bring it to here. Why? Because, for instance, if some clients went already to a lot of to some movies before, then they will probably not go to next day to another movie. So their tendency would be to lower their participation. On the other hand, look what happens here. If the price is here, then the number of buyers is very small. So the producer will say, what about just a little bit lowering the price? Then I'm increasing in a macroscopic way my sales. So it's in my interest that I lower the price such that I'm getting someplace here where with a very small change in price, I'm getting a very macroscopic increase in my sales. Of course, after he gets here, it's not anymore so advantageous because this line is going down here. So it is the very pricing process and the very buying process are conducting to the fact that the markets are quite typically in the region in which you have this, in the critical region, and therefore in the region in which you have very large fluctuations in the prices. So this is what happens. And also, you have the model is predicting also the existence of this fractal island, which we have seen that it happens in nature too. And also there are some power laws appearing of the type that we are discussing, but which I don't have time to discuss now. So now let's discuss the decreasing returns case, which is also relevant for adopting green technology, in which I said it's in a sense typical of or similar to what happens with software, because as in the case of software, there is a very high investment at the beginning, and then if you are spreading it over 100 people, then and you invested $1 billion, then it's very expensive. But once you have very, very many buyers, then you can afford to sell it with a much lower price. So in place of having decreasing returns, which means increasing price with the quantity, you have decreasing. And now, let's put together this line, which we have just studied, except that now in place of having this line, I have this line. With this new situation, of course, this line can have different positions. In some of the positions, you can have one intersection. In some of them, you have 2 intersections. In some of them, you have no intersection even at all. What does it mean that there is no intersection? It means that the price at which you are trying to sell, it's pretty affordable for most of the people. And, or rather, the initial price is not affordable. But because you keep selling, you are getting to a lower price. And even when you get to a number of people, to people which are pretty poor and they cannot afford the initial price here, by now the price went down enough, and the entire process can go on. We'll see that it doesn't go on to infinity. It has to stop someplace because of the finite effects. But for the moment, I want to emphasize this, what happens here, that because of this particular shape of the demand curve, you have a situation in which you see at the beginning you are selling relatively fast, but here you are selling very little. You just increase in one single step. You increase the number of buyers with just a little bit. Because of this, the price decreases by a little bit, and because of this, the number of new buyers is only very few. And so on. So you have a certain region here which is predicted by this kind of percolation combination between combination with the percolation transition, in which you are saying at the beginning the product can start pretty well, but then you might have some decrease in the sales, and only then taking over or not. And indeed, this kind of thing. So you are predicting, if you think in terms of sales per time step. So at the beginning, you have some sales at the beginning, and then and then they increase. But then you get to this narrow region between the two lines where they decrease very much. And in fact, if you are not lucky and the blue line really gets tangent to the red line, then it stops. But if not, you just have this thing which is called saddle, and then only then it goes on. And so you have this kind of things which happens even in nature. But before that, this is what happens if you change just a little bit in a simulation of the system. You know, a percolation simulation with all this mechanism which I described. This run was done with a red line tuned with the initial, because essentially the height of the red line is dictated by the initial price. So if you start with an initial price which is just a little bit below some value, then you go down here, but then you take over. And if you just increase a little bit more the initial price, then you actually get stuck there. So this is the kind of things which can help decision makers to identify these points and to try to help. So this what happens if the red line, in place of being below the blue line, it's actually here. Then what happens if you have quite a number of different regions? Which we can understand now with the help of our just a second. Okay, so if you start here, then you will go on, because the blue line is above the red line. So what they are actually, the colors have changed. But this is demand, and this is the offer. So this is the implicit. This is the price of the market, and this is the implicit price, which is dictated by how many people have bought. So if you start here, then you go here, and then you go here, and then you convert here. So this is a case in which you stop at a finite value. Then there is this entire region in which, if you look, if anything, you are actually losing buyers, if you really take it seriously. So you are losing buyers, then you have to increase the price, then you are losing even more, and then you are converging to this point too. So this region is a dangerous region. One needs subsidies here. On the other hand, if you have already this number of, if you impose this number of buyers, or somewhat you keep the price fixed to this value until everybody which wants to buy at this value buys. So if by some method you are getting to this point, then this is self-sustaining already. But as you see, it will still stop, because this finite part of the because essentially the number of buyers cannot be larger than the potential number of buyers. So the finiteness of the system appears. So it will stop here. So there is always some resistant core, which has nothing to do with the percolation. It has to do with the fact that they wouldn't buy even if they know from the beginning, and even after the price has went down because of all the others bought. But this is the region essentially of propagation. And then you start asking, okay, so how do I get to this region? How do I get the product to be adopted by most of the population? I have to subsidize. And I know exactly by what to subsidize, because this is the price which people are, this is the market price, and this is a price which people for a certain N are willing to pay. And so if you make the difference between these two prices, it tells you what is the schedule of subsidies, the minimal schedule of subsidies which you have to give in order to get to this propagation region. And as you see, this is quite important information, because if you take all this money in this region and put it here, that's not good enough. Or if you take all this money and you spread it uniformly, that's also not good enough. This is a way to find what is the optimal schedule for subsidies. Moreover, there is some other understanding which comes from this model, which is the following. Just a second. No. Is the following. Suppose that I brought the price here, or I brought the number of buyers here. Now, what do I expect? That I'm out, I'm happy, everything looks beautiful. It's not so, because you see the initial steps are very small. So even after giving, for some reason it doesn't appear, even after giving the subsidies here, it takes a very long time in time. It's not really fair to put this graph on the same graph here. But it takes, you know, these steps, if I make them in time, then for a very long while, the initial steps are very small, and only after that you get the triggering of the percolation transition. So at the beginning, you are just still going slow. So that's another policy important information, that the fact that you don't see the results immediately you should look carefully what's going on. And if you look microscopically, like in the case of the AB model, then you see that there is some activity in some place which is really advancing, and that you might afford not to intervene. But again, you have to understand how this number of buyers increases. If it increases by just some sparse guys which happen to, I don't know, to have some crazy idea, then it's not good news. But if you have a small region which is slowly expanding by this kind of cactus paradigm which we discussed in the percolation lecture, then you say, oh, I mean, the process is going on, even if it is still microscopic at the beginning. Okay, so now I for some reason today I was much slower than before. Now I'm going to describe, as I said, the application to the formation of the price. It's just one possible application, but the same kind of mechanism, for instance, can be applied to, for instance, the mechanism of loans and interest rate. And this will help us to understand how the world got into trouble and reach the point in 2007, 2008 of this collapse, and what happened after that. So let me explain. This I is essentially the interest rate, which is essentially the price of loans. And N is the number of loans. So now N is not a product, it's a quantity of loans. And the price is not the usual price for a car, but it's the interest rate. You know what is the interest rate? How much you have to pay per month for a certain loan. So you, in theory, as long as in order to get the loan, the bank would have to actually have some gold or some reserves which justify that money and say, okay, I give you that money. There was an decreasing return. More they would have to give, more difficult would be to gather that money, and therefore this was a line which in which I, or the price, went up with the number of loans. And of course the demand would go down, that's normal. However, what happened for a very long while before 2007, 2008, is that the mere fact that a bank gave a loan to somebody, this would be considered an asset. Like you signed that you owe them $1 million, even though you didn't get, they didn't have to actually have them into their coffers. And because of that, actually what happens is that this line became increasing returns. More loans they gave, more they could afford to give an interest rate which was lower. So you have now, we are now in the situation in which you have this demand, which is, of course, the number of loans demanded goes down with the interest rate. But we have a situation in which the interest rate actually goes down with the number of loans. So you have these two lines. And then look what happens. If there is one bank which is giving very few loans and at very high, it's conservative. It gives only to the guys which are really, trustful. Then it will this iterative process which we are discussing. If the slope, this slope is higher than this, then you'll have a situation in which those banks will give less and less loans with higher and higher interest rates. On the other hand, the ones which are starting to give large loans beyond a certain critical point, then they will afford to give even lower interest rates, which would bring them more clients. Having more clients, they have formally at least more assets, and you will have a situation in which the number of loans will increase and the interest rate will be pretty low. So in a sense, this period was a posteriori called by some of the economists irrational exuberance. But from the point of view of the individual lender, it wasn't irrational at all. It has the choice between being cornered out of the market and having forced to, because of that, to charge higher rates, and because of that being even more isolated from the market, and between giving irrationally low interest large loans, even to people which weren't very qualified, and keeping itself in the market, and in fact increasing the volume of their business. Is it clear? Okay.
I don't understand why. I mean, if the bank is in a situation where it can give out more loans,
yes,
it has no reason to lower its interest rates.
Yes,
So
the point is the point is the following: in the moment that the fact that you own them money is considered as a leverage for getting 10 times more money from the central bank in credits because they have this asset, and then it's their interest to attract you to lend from them 1 million, because with that 1 million they will get a loan of 10 million from the central bank, which they will be able to lend to other people too. Is it understood? Okay, so it's a part of, actually I would have expected you, because you were exposed to economics. The point is the following: a bank in that times, and even now, is allowed to give loans which is actually more than 10 times the actual asset which it has. Okay?
Yes, but that's regulated by law.
What?
That's regulated by law.
Yes. But this means that giving to you 1 million, they will get the possibility to lend another 10 million. Therefore, that
didn't change. It's not something that happened before 2008. It doesn't happen now. Or
it didn't. That's something else.
Steady market. It's not.
That's something else that it didn't change. Of course, it didn't change. What changed is that people which were taking these loans, some of them started not to give back the loans. Wait. Meantime, this is a mechanism which happened. Do you have problems with this mechanism?
I don't understand. I mean, if people were loaning the same amount beforehand, what happened in 2008?
That definitely, I cannot explain both what happened before and after in the same moment. Meantime, I'm claiming this is what happened in until 2007, 2008. Okay? Now I will explain to you what happened after that. It's the next slide. So I'm, in a sense, I'm not even trying whether you agree, because there are always some economists who don't agree with the standard. This is a standard explanation, by the way. It's just casted in this formalism which we are discussing. So the question is whether you understand the statement, not whether you think that this is what exactly happened. Okay?
I just don't think it's logical.
Well, a posteriori, I mean, you are together with, I don't know who called it irrational exuberance. I forgot the name. But I think that Greenspan had also some other name which was nice. So in any case, these power laws, we measured them for the companies in Italy, so they are pretty safe. And now let's see what happens. Indeed, at some stage, what happened is that there were all these companies with a lot of loans, and many of them, they had loans which actually, if you really looked at it, they didn't have enough income to pay them. The only way they were paying them is by making more loans. And they were able to make these loans because the banks weren't checking that they are actually red. That they were, what technically this is called Ponzi. Even Ponzi was some guy which actually deliberately did that in the, I think in the 20s. He wanted to make a business of importing some stamps from Italy to the United States. It became clear that it will not work, but people kept investing in his stuff. So he kept, with the new investment, he kept paying the interest which he promised to the guys which already invested. So the thing went on a lot until when? Until until he couldn't pay anymore. So this is why such companies are called Ponzi. But for a while they are not discovered. Typically they are discovered when some of their partners are in trouble, and then people start looking more closely to their business, like in the case of Madoff. So we have this kind of contagion. So now I see that I don't have much time. The point is that you have the same thing. The number of as you have more companies failing, the interest rate will increase, because the banks will not want to risk their money anymore. So you have an inverse feedback loop in which you have the interest rate going up with the number of failed companies, and but then the number of companies which are in the position of not being able to pay their interest would increase with the interest rate, because with the same loan and with a higher interest rate, now you are in the situation that you cannot pay it anymore. So you have again this kind of either equilibrium or disequilibrium, in which you see that above a certain range of bankruptcies and depending on this exponent, you might have a situation in which you have propagating, macroscopically propagating percolation of the crisis. And when you put it together again with this graph, instead of taking the straight lines, we take this graph, then essentially you have, this is a percolation line, so instead of a straight line you have this. And when you put together this line which characterizes the increase in the interest rate together with the dependence on the number of bankruptcies with the interest rate, then you have again this kind of graphic thing which can be transformed into analytical solution, and which tells you that what are the regions which are dangerous and what not. For instance, in this region, even if you have a lot of bankruptcies, they will actually heal themselves if you allow them, or at least they will not propagate, because you see the iterating process is going to lower and lower interest rate and lower bankruptcies. However, if you are beyond this point, then you are getting into this percolation of the crisis. Of course, at some so now you can, as a function of the different parameters, you can this region, this region, and this region, they become these regions here. This is the micro crisis. The region. This is the crisis. This is the part which is stable. This is a part in which we have the percolation of the crisis, and this is the part which we had here, in which they are already the guys which are stable anyway. Now, in terms of policy, what happens is the following. If one is in the stable stage, but very close to a situation in which very many companies got too much loans, then typically the government will say, okay, let's increase the interest rate, they will take less loans, and the situation will become more stable. And if they do this, they indeed could get into this region in which there is a little avalanche of the most most endangered companies, the ones which were most irresponsible, and then it stops. However, if they overdo it, and very often this is what happened historically, then they get in this region in which the bankruptcies of the first wave, they are increasing the interest rate, they are putting other companies which were relatively okay until that moment into more danger, and you have the entire system, or a very large part of the system collapsing. And now that the entire system collapsed, we can stop. I thank you very much for your attention.
Thank you.
Bye.